We're going to start by talking about some fundamental properties of matter that you're already familiar with, and that is charges. You know that in an atom we talk about the nucleus having a positive central charge made up of protons and neutrons, and then we talk about electrons often in orbits going around. You probably heard about that in chemistry, but really it's about an electron cloud. Quantum mechanically, but we can think of the electron as having a negative charge. So the charge of an electron is minus 1.6 times 10 to the minus 19th coulombs. So our unit of charge is a coulomb. So if something has a charge of 1 coulomb, that means it's got lots and lots of electrons, extra electrons, or it's missing that many electrons. And so that's the electron. The charge on a proton is positive 1.6 times 10 to the minus 16 coulombs. So charge is quantized. It comes in these discrete units, but we often talk about just an object having this many nanocoulombs, 10 to the minus 19th coulombs, for example. And so in general, when we think about electricity, you already have lots of experience with electricity, but electricity is moving charges. And when we think about moving charges, we think about charges moving in metal, right? So our wires are metal because these are conductors. And what happens at the atomic level in conductors is that electrons are not particularly localized to the atom in sort of this picture. Once they get into a solid, there are outer shell electrons that can really move. They're sort of shared over the whole material. And so conductors, metal conductors, are things where electrons can move easily. You can think of there being some free electrons that can just slosh from one end of the metal to another. And then we can think of insulators, like plastic. The typical one would be a plastic, but lots of things are. And this is where the electrons are tightly bound to the atom, so they can't move around. They can't sort of get loose of their atom at that point. They can move a little bit, but they don't wander through the material. And so when we have a cable, for example, we have the inner part where the electricity flows. So we've got a flow of electrons for our electricity in our conductor. And then outside of it is our plastic insulator layer, so that when we touch it, because we're not terrible conductors, we don't have electricity going through us, or so that this conductor doesn't connect with something else and the electricity goes to some place besides, say, charging up your phone, which is where you wanted the electricity to go. Okay, so how do we get things charged up? There are a couple ways to do it. One is sort of just rubbing materials together. So one is really by friction. You see this when you pull clothes out of the dryer and they want to stick together, the static cling. What you're really doing is you're rubbing electrons off of by tumbling in the dryer. Electrons get rubbed off of one material and onto another. So you have one material that has extra electrons and one that is missing electrons, so that would be positively charged. And for materials that we're familiar with, ones like a PVC pipe, for example, and silk. You'll see an example of that. When you rub silk on PVC, what happens is extra electrons get delivered to the PVC and positive charges are on the silk, and then they're both charged. This one's negatively charged, this one's positively charged, so they want to stick together. And that's what happens to your clothes when you wash dry clothes of different material. And so that's one way we can charge things up. We can charge things up by bringing, so this is by induction, is what it's called. And of course, we know that opposite charges attract, like charges repel each other. So by induction, we take something like our PVC, our charged PVC, and we put it near two conductors. So these are two, say, metal spheres that are in contact. And when this negative comes by, what happens is this, even though these are neutral, this gets, the charge gets attracted because charges can move. So the electrons that were sitting in this part of the material, equal numbers of electrons and positive charges, protons, the electrons head over this way because they are repelled by this, which leaves behind some positive charge. So we get charge separation, okay? So even though I have something that's neutral, notice right here, I can have something that's neutral. If I can spell it, something that's neutral can be attracted to a charged object, right? Because of this charge separation. And then all we have to do is carefully, we don't touch them, obviously. They need to be on top of an insulator. This is usually the way we draw these insulator stands. So some sort of plastic that it's sitting on. So we separate these. And so we move one of these off to the side a little bit. And it's still got its charge. So we move this one away a little bit. And there we go. While this PVC is still here. Now we've stranded these charges. They can't move around. This is positively charged. This is negatively charged. This is the way they're happy when the PVC is here. But when we remove the PVC, then these positive charges are like, I don't want to be near each other. So they spread out. Maybe we have extras. These spread out as well. In fact, in this case, if they stay next to each other, in fact, what happens is the electrons get pushed around and we get an excess charge over here, and these are attracted to each other. If they get moved away from each other, then the charges get evenly distributed on the conductor. So that's one way we can charge things up if we have two objects. If we only have one object, we can do basically a similar trick. So here we start with our PVC again. PVC. Again, a conductor. Okay, so this is metal right here on a stand. But I don't have a second piece of metal. So what happens is the charge gets separated right like this. So again, a conductor, the charges separate. And in this case, what we do is we go through the following steps. We take a wire and we connect it to ground, to the earth. Now, ground is a location. We think of this as a place where we can get charges, or we can dump charges. It's sort of an infinite sink or source of charges in our model. And this is why, for example, when you have lightning rods on buildings, basically you have a conductor on the top of the building. It's the highest point, but it's connected to the ground so that when you have charge that needs someplace to go, it can hit that lightning rod and go around the building to the ground instead of going through the building. Okay, so ground gives us a place, and these extra electrons right over here are like, I do not want to be here because I'm still repelled. So these go rolling off, and so I roll them off of the conductor like so, and they're in the ground. So they're down here, and they're just extra in the ground, and the ground can accommodate lots of extra charge. And then what we do is we set things up. So then we remove the ground. Okay, so we've run all those off. We remove the ground. Okay, it has those extra charges. The positive charges are still here. They're happy. And then I can finally remove my PVC. And again, I'm left with a metal that is now charged, and these positive charges want to rearrange themselves in the metal. Like this, to get away from each other. I mean, it's not really positive charges that move around. Of course, it's negative charges that readjust so that positive charges show up sort of as far away from each other. So what we've used is that charges that are opposite in nature are attracted to each other. So these are attracted. But we've also used this fact that neutral objects can be attracted to a charged object. So again, if I have my PVC here, even if I have something that's neutral, so this is neutral, if it's a conductor, then we get charge separation. If it's an insulator, so this is conductor. If it's an insulator though, so a PVC like this, with an insulator, what happens is even though the electrons can't leave, we get sort of a shift. Instead of a circular, we get sort of an oblong, we get what's called a dipole moment, and so we get a little bit of a shift. It's not as big an effect, but we get this sort of shift all the way along here. So it looks like we have a little bit of extra plus charge over here and a little bit of extra minus charge. This is called polarization. And this shift is what allows things like balloons that are charged up by rubbing them on your head can then stick on the wall. The wall is an insulator, so we get this polarization of charges, and the balloon that's charged can then stick there.